Okay. Okay. So, yeah. So, welcome to the week 7 of the problem solving session for the design and analysis of algorithms course. So, last time what we saw is this paradigm called greedy algorithms, and yeah, and we saw how to use this strategy for say Huffman coding and so on. And although we didn't get time to look into the correctness of the algorithms, if you would like to look into, I think, yeah, with I mean the standard references, which is Coleman or Tartush and so on, you can look into it. So this week what we'll do is we'll look into this paradigm of dynamic programming. So okay, so both the strategies have something in common, but there's something that is different with them. So for example, in both of them, what we're going to do is we're going to solve some subproblems and use the solutions optimal solution to the subproblem to build an optimal solution for the original problem. So one property is that we can use the optimal solution for subproblems to build optimal solution for the original problem. Okay, so what do we mean by that? For example, we saw one such algorithm which was APSP, all pair shortest path, which is due to Floyd-Warshall. And what we saw here was that we want to find shortest path. So the notion of optimality here is we want to minimize the length of the path from any node, from any source to from given source to given target. So what we instead do is, if I want to find so there's some graph that is given to us, and yeah, so let's say there's some graph that is given to us, and what I want to do is I want to find shortest paths from any node to any node. Let's say I'm looking at SNT, the given SNT for now. Then what you do is you actually think of think of these as being labeled from 1 to n, 1 2 3 4 5 6 7 8 9 10. So then what you do is you think of this shortest path as going from node S to some node T, to some node P, and from P to some node T, where you want to minimize the distance from S to P and the distance from P to T. Or it may so happen that it does not even take the node P, and there is some other path that is shortest. So we are used the kind of sub problem that we identified here was the shortest path to some other node. Okay, so how do we get this into account? So okay, maybe for the sake of simplicity, maybe just let me call this 10 and this one is 5. So I want to find the shortest path from S to T, which is from 1 to 10. Then what I'm going to do is I'm gonna say that first let me find the shortest path from this S to from 1 to 10, which uses the node 2, or it may not use the node 2. So I'll just I'll just say that shortest path from okay, I'll just erase this for the sake of I'll just add one more parameter here. So when I say ijk, I mean that it's a path from I to j, which has only used at most k many at most k nodes. By k nodes we mean it can use these 1 2 and so on up to k, but using other nodes is not allowed. So how do we do that? So this path can either be a shortest path. So we are saying the shortest path can either be shortest path from I to k and then a shortest path from k to j, or it can simply be a path from I to j which does not use k. So it's the minimum of shortest path from I to k plus shortest path from k to j, or it's just simply the path from I to j. Sorry, let me write this. I to k using nodes up to k plus shortest path from k to j using nodes up to k, or it's simply the shortest path from I to j by using up to k minus 1 nodes, because it does not use the k node. So this is something we did earlier, so I'm not gonna get into it, but it's just a quick recap of what we did earlier. So what we're doing is you are sort of solving for the smaller and smaller subproblems and using it to build a solution. So what we'll do today is some other examples of this. Okay, because this is something we did earlier. So let me just get started with the first example. So okay, so let's say you have been given, this is called the maximum subarray sum problem. Okay, so the input to you is an array whose entries are integers. So let me just give an example. So let's say you have -2, 3, 5, -6, 1. Okay, then you have, let's say, 7, -3, 5, 6, -2. Let's say this is the array that is given to you, and what you want to find is so what is a subarray here? A subarray is a contiguous block, a small array sitting inside it, but it has to be contiguous. So it cannot be, for example, 3, 5 and then 7. This is not a subarray. A subarray would look like this or this, something like that. It's a contiguous block of a chunk of array sitting inside. What you want to output is, so if I look at this particular subarray, then the sum of this subarray is simply the sum of the entries or values that are in there. So this would be 3 plus 5 minus 6 plus 1, so which is 3. So the sum of this subarray is 3. If I look at this subarray, then the sum is 4. So the question is, what is the maximum sum that you can get inside the array that is given to you? So find a subarray and find the sum, and it should be the maximum of all the sums of subarrays that are there. So so maybe just for this example, what is the maximum sum of the maximum subarray sum that you can find? If you just, trivially try out, right now we are not asking for a dynamic programming solution or anything. If you just try out, what do you get? Is the question clear? Is the question clear? Can if there are any questions, then please ask right now. Okay, so the answer for this is 16, which maybe we'll figure out how to find this with the DP solution, but I hope the question is clear at least. If not, then ask me at any point. Okay, so let's see what is a okay, so what is a very trivial solution, even before we get into the dynamic programming algorithm and all. What is the Um, yeah, what is a trivial solution for this? Anusha, Pujita, and um, Varshinu, I think. Sorry if I'm pronouncing it incorrectly. So, if you have any thoughts, then please interact. That would help me present better. Okay, so let's see, even without getting into the dynamic program and stuff, let's see what is a very trivial algorithm for this. So, what is a trivial algorithm? It is that you look for, it says that you find a subarray, find its sum, and then check for which is the maximum. So, then what is a trivial solution, a trivial algorithm? Trivial algorithm would be that, yeah, go through each subarray and find the sum of the subarray and maintain a current max sum, and if the current sum is larger than the maximum, then you are going to update the maximum to equal to the current sum, and then you simply repeat this until no subarray is remaining, right? So this is the trivial algorithm, that is you're going to check every subarray, that is you're going to check through this, you're going to check through this, then and so on, these kinds of blocks. Then there are blocks of 2s like this, then there are blocks of 3s like this. So how many such subarrays would there be, like roughly asymptotically, if you want to bound, how many subarrays would be there? I mean, any random guess? Would it be n square or n cube? Okay, so maybe let's find this out. So how many subarrays are there? So if you look at, I want to understand the time complexity of this. So then what I'll do is I'll find what are the total number of subarrays that are possible. So let's look at this array of size n. You have 1, 2, and so on up to n. Then my subarray could be of size 1. So it could just be this, it could just be this, and so on. So how many subarrays are there? Subarray size and number of subarrays of that size. So if I take my size to be 1, then there are exactly n many subarrays, because this is precisely what the answer is. But if I take my subarray size to be 2, then how many subarrays can there be? Well, 1 comma 2 is one possibility, 1 2 is one possibility, 2 3 is another possibility, 3 4 is another possibility, and so on up to n minus 1 comma n. This is the final possibility. So how many of these are there? These are n minus 1. So I'll write n minus 1 here. Similarly, if I take subarray of size 3, then what is the total number of subarrays that you can have? You can use the chat if you have any answers, or you can even unmute and speak.
Ma'am, NC3.
NC3. Okay, but we are looking at continuous subarrays, no? So, for example, this is one, sorry, I'll just use another pen. So, this is one subarray, which is 1 2 3. Then 2 3 4 is another subarray. So, I'll just write this down: 1 2 3, 2 3 4. You can start at 3 3 4 5, 4 5 6, And like that, what will the final
n minus 2.
n minus 2. Good. Yeah. So this is n minus 2. In general, if I take a subarray of size k, then what will be the number of subarrays? So it will be n minus k plus 1. Why is that? Why is this happening? Because my subarray of size k, if it starts at 1, it will be a block of size k. That is the only subarray that we can have which starts at 1. If I start at 2, then it will be a block like this, just one block ahead. It's just shifting one block ahead, and so on. If I start at 3, it will be like this. So for example, I cannot start at n and get a block of size k starting from here, because there is nothing behind, and there's nothing after it. Similarly, if I start at n minus 1, I can't get a larger chunk. So what is the last position where? So just count k blocks starting from n, start counting k blocks to the left and find that index. So this will be n minus k plus 1. And if you go at n minus k plus 2, which is here, you can't find a block of k because the array ends there. So there is one subarray starting at 1, there is another subarray starting at 2, and yeah, and finally there is one subarray starting at n minus k plus 1. And that's why when you when you get to n, there will be exactly one subarray of size 1, which is what is given to you. So yeah, so that is the, yeah, that is the count. And so if we sum them up, what is this? Okay, so is everyone with me? Is everybody clear with, or does everybody agree that this is precisely the number of subarrays of that particular size? Okay, if you would want me to repeat anything, then please feel free to ask. Don't hesitate. Okay, so okay, so then I know that the number of subarray of size 1 is n, size 2 is n minus 1, and so on. So I just have to sum them up. So total number of subarrays is simply 1 plus 2 plus 3 and so on up to n, which is nothing but n into n minus 1 by 2, which is order n square. So this is something you know from the previous, I think the some week 3 or 4, I think sometime we did this. So anyway, this is an identity. So you get like a quadratic number of subarrays. So what you do is you have order n square many subarrays here. Finding the sum, how much time does it take? So if I give you a subarray and I tell you to find the sum, it will take at most linear time, right? Yeah. And then what we're going to do is, once you find the current sum, if it's greater than the current maximum that you're maintaining, then you will just update it and keep on doing this. So this will roughly be like order n cube or even order n square if you do a good analysis. So this is a trivial order n square time algorithm, which is very easy, like very very obvious thing to do, right? You just go through all subarrays, find which is the maximum. So there's nothing clever happening here. Okay, so now what we want to do is we want to use our dynamic programming approach to solve this. That means I want to build some sub problems. I want to use small sub problems, solve them, use their solution to find the solution for the whole, for the entire subarray. Okay, so yeah, so can you think of some strategy? So okay, so let me first describe one strategy which is not optimal, which will also take order and square time. After that, we will see how to improve it to linear. We will bring it down all the way to linear. So let's just quickly see how to just think of a very obvious way of doing a dynamic programming approach. So I want to use dynamic programming, and what I'll do is I'm going to maintain a table, which is what you must have seen in the examples that you saw in the lectures, which is say edit distance or the grids or anything. So you maintain some sort of a table, and in this case, the table could be maybe I'm storing my end index and a start index. So what do I mean by that? So let me write that 1 2 3 4 5 1 2 3 4 5 6. Okay, so what that means is let's say I have an array here of size 6. So 1 2 3 4 5 6, and minus 2 3 7 minus 1 3 minus 4. So let's say this is an array of size 6, and what does this table represent? This table represents, if I look at a row and a column, what that means is I'm looking at subarray starting at 1 and ending at 3, which is this in this case. And what will I store here? I'll store the sum of that subarray. So if I say 1 to 1, that is this subarray. What is the value stored at that? The value is minus 2. Similarly, if I look at 1 comma 2, then what is the subarray? It is the subarray which starts at 1 and ends at 2. So what will be the value? The value will be the sum of these two, which is 1. Now can you quickly like tell me what are the values in this row? What should be 1 comma 3? Okay, so 1 comma 3 is basically the sum of these, but what I'm going to do is I'm not going to now find minus 2 plus 3 plus 7. I'll not do that, because I already know the sum of 1 to 2, which is 1. So I already know this sum, this is 1. Now I'll just add 7 to it and write an 8. Similarly, if I want to find a solution for 1 to 4, I'll not start adding minus 2 plus 3 plus 7 plus minus 1. Why? Because I've already found this solution. What is that? The sum is 8. So if I sum all the way up to this, it will be 8 minus 1, which is 7. And similarly, now if I want to do the sum of 1 to 5, I'll not count all of them. I'll just look at the previous sum and I'll add it to the current value, that is 10. And similarly for 6, it will be 10 minus 4, which is 6. So I'll write this 8 7 10 6. Now notice that the left diagonal here is useless. So this part of the matrix is useless, because it does not mean anything to say that the array starts here and ends at 1, or it starts at 5 and ends at, because we always go from left to right. So all these values are anyway redundant, so you can assume that these are zeros. I'll just cross off this part. I'm only going to look at this part of the table. Only these are the values that matter. So can you now tell me what is the value at 2 comma 2?
3.
3, exactly. And now if I want to, good, so now if I want to find the value at 2 3, then how do I find that?
10.
10. So how did we find? You just looked at the previous sum and just added the element 7 to it. So you get a 10 here. And now if I want to find for this, we'll just add 10 with minus 1. So what are the entries?
9, 12,
9,
8.
sorry, yeah, sorry, what was it? Yeah, 9, 12, 8. Good. Similarly, can you tell me the remaining values now quickly? 7,
695.
9, 5. Good. Then minus 1.
Minus
Hmm.
2 minus 2.
Minus 2.
3 minus 1.
3 minus 1. And
Minus
finally
4.
minus 4. Okay. So now what is the maximum number that is there in the whole um, triangle?
12, man.
12. And so what is the subarray corresponding to it? I look at the row, I look at the column. It says 2 to 5. So 2 to 5, this is the subarray which has the maximum sum. So if you do this method, it's even if you just look at if you just look at the values, there is a way to trace back what is the subarray. So the question only asks you to find the maximum sum. It does not ask you to tell the subarray, but the way you are designing the algorithm, there is a natural way to extend it to get uh, to the subarray also. This similar thing you have seen in the shortest path algorithm also. I'm just uh, I'm just recalling in case you can make the connection. If not, it's okay. So what we did in the shortest path algorithm was we sort of started writing these values one after the other, and we were looking for the shortest path by just taking shortest edge which satisfies certain constraints, and then we had a way to just use that value to trace back the entire path. So we didn't do anything special in the whole thing to get the path, but the way we designed the algorithm gave us a way to extract the shortest path. So something similar is happening here. So yeah, so good. So what is the running time of this algorithm? So although I'm doing some sort of a saving, I'm not like adding over and over again. Still I'm doing some sort of non-trivial operations. So what is the running time of this? Okay, so let's find out. So what I'm doing at every step is, um, I'm looking at this value. I'm just adding one element to it and writing this. I'm just adding one element to this, adding this. So basically, what we're doing is at every step we are just doing a sum of two numbers. The sum of two numbers is something you can assume you can do in constant time. So for writing every entry, it took you constant time. Okay. So now how many entries are there in the matrix? If it's of size 1 to n, it's an n cross n matrix, then how many non-zero entries are there in terms of n? You can just tell me like in terms of order. It's you don't need to tell me exact number. You can even tell in terms of order. So is it linear or is it quadratic? Is it cubic or okay? So
Order of n square.
it's order of n square, exactly. So this is order of n square, and that means you are not really doing saving in terms of time. Maybe there is some constant factor we are saving, but we are not doing much of a saving by doing this algorithm. Um, what I want is like order n time algorithm. Okay, so this is a very okay. So just to reiterate, so this is a very obvious thing to do, and it also gives you the correct answer always. And it's a dynamic programming strategy, which is which is clear. But what I'm not happy about is the running time of the algorithm, and that's why we want to do something better. So, do you see some kind of redundant calculation that we are doing, or something that we could have avoided and saved on time? Okay, so let's see how to do this. So let me just take the previous. So let me just take the example first. After that, we will write the algorithm. So I'll just take this example from here. So okay, so I'll just erase. Okay, okay. So now what we'll do is, yeah. So now what we'll do is we'll make the following observation. Okay, if there is a subarray, the subarray has to end either at 1 or at 2 or at 3 or at 4, or basically it can end at any of these points. So this is something very common. I mean, it's very obvious, but we will see how we are going to use this very obvious fact to save on time. So the observation is very simple to make. Observation is that the subarray ends at an index I in n, at some index I in n. So what I'm going to do is, I'm going to the sub problem that I'm going to solve is that I will find out what is the maximum sum of subarray that ends at I. Okay, so it could start anywhere. So let's say my I is 5. It could start at 1, it could start anywhere here. I don't care where it started. I'm just going to maintain what is the maximum sum that ends at 5. It may be starting from 2, it may be starting from 1. We don't care about that. Why are we doing this? Because notice that we'll make another small observation. We'll see why these observations are useful. This is also a very simple observation. 2 is also very simple. So let's look at my first element. Okay, what is the value? The value is -2. So when I make a subarray which has a maximum sum, should I include 1 or should I exclude? Should I include this or should I just start my exploration from here? So can it ever be that a maximum subarray started at 1 and ended somewhere else? For this particular example. So how many of you think it's possible? You can use thumbs up or emojis or whatever, or use the chat. I just want to understand whether you are with me. So can it happen that it starts at 1? Anybody who thinks no? Okay, so let's see. So you cannot start at 1. So in this particular case, I'm saying you cannot start at index 1 because the value is -2. So if there is a subarray like this here, if there is some subarray here, let's say which has a sum of 10, okay, and let me just write it. Maybe this is the maximum subarray, it has a sum of, I'm not, okay, what is the exact sum here? 8, 9, this is 3. Okay, maybe let me take this whole thing. 3 plus 7, this is 10. Okay, then I should definitely not include 1 here. If I include this index also, then the sum becomes 8. So having a negative number here is only going to decrease the value of my the sum of my subarray. It's never going to increase. So if there is a subarray with some sum, I should just avoid the negative one in the beginning. I'm saying, not anywhere in the middle. It cannot happen anywhere in the middle. Just in the beginning you cannot take a minus 2. Okay, so these are the two simple observations that we are going to use to build our entire solution. So how do we do that? Notice that if I start at if I start at 1, then what is the maximum sum I'm getting at this point? What is the maximum sum of any subarray that ends at 1? What is that? It is minus 2. Okay, and then let me look at 1 comma 2. So what is the maximum sum of any subarray that ends at 2? So what are the subarrays that end at 2? It is either 1 comma 2 or it is simply 2. If it's 1 comma 2, then what is the sum? The sum is 1, right? And if it is simply just the subarray of 2, then the sum is 3. So we are looking at maximum of the subarray 1, 2 and simply the subarray 2. Let me say sum of this. So sum of 1, 2 is 1, sum of 2 is just 3. So which is the maximum one? It is 3. So I'll write 3 here. Okay, similarly I'll do the same for the subarray 1, 2, 3. So what is the maximum sum of a subarray that ends at 3? Here is where we are going to use our observation, which is if there is a subarray that ends at 3, then I look at the maximum sum that I had up to point 2. I'll not really look at all the values earlier. I'll just look at the maximum sum that I had up to index 2. If adding that with 5 increases my sum, then I'll keep it. Otherwise, I'll simply start at 3. So in this case, what happens is, what is the maximum sum up to 2? It is 3. So if I add 3 and 5, then so maximum sum up to this point is that of 3. 3 plus 5 or 5. I'm going to take the maximum of this. So this is 8 and this is 5. So maximum is 8. So I'll take it. Okay. Now similarly, what about 4? What about 4? So what is the maximum subarray sum that ends at 4? You look at the maximum you had until 3, which is 8. Now I'll add minus 6 to it. That will make the sum 2. So 8 minus 6 comma minus 6, which is the maximum of this 2. The maximum is 6. So this is 2. So can you tell me the remaining values? Okay, so yeah, so let us write the remaining values quickly.
3 it will be.
Okay, good. So 2 plus 1 is 3. Then you get 10. Then you get 7. Yeah, can you tell the remaining?
Twelve, 17.
12, 18,
Yeah, sorry, 18.
18, and then 16.
Uh,
Yeah, so what is the maximum value here? The maximum is 18. Right, so the maximum is 18, and what does it tell you? It ends at 9. So yeah, so this value ends at 9. And what is the subarray? The subarray is, I think, this one, which starts at 5 and ends at 9. So if you sum the numbers from 5 to 9, then then this will turn out to be 18. And so where did we use these two observations? Notice that Okay, sorry. Maybe I think I did I make a mistake? Mm, yeah, sorry. You do from 2 to 9. Yeah, yeah. You do from 2 to 9, then you get 18. Okay. So where did we use the fact that uh, yeah, I mean, the first and the second observation, the second observation we used when what happens is, if at some point, which it did not happen in this case, but if at some point this sum becomes negative, let's say this becomes -6, then what I'll do is I would rather not take it, and I'll start by taking my new element itself. So yeah, I think it happened at this point, or some point, I think. Okay, maybe I'm not sure if it happened in this example, but this is precisely what we're using. So if the consecutive sum until some point is negative, then there's no point in taking that subarray. I'd rather start by starting a new subarray search. And where did we use this? We use this to uh, avoid solving this all the way everywhere. We just used, okay, what was the previous maximum, then I should add the new element, whether that gives me the new maximum, or should I just simply start where I am. So how much time does this take? What are the operations that we did? We just we just wrote this sum. That is all we did. So what are the operations we used? What is the time that it took? You can just tell me in terms of order. You need not tell me exact expression. So at every point, what are the kind of checks that we are doing? We are checking, let's say I want to find at 4. I'm just looking at the value at 3 and adding it to the value at 4 in the given array, finding the sum, checking whether the sum is, finding the maximum between the sum and the element's value itself. So this is just an order one operation. You are just adding two elements and checking for the maximum. This is something you can do in order one time per entry. Okay, and how many entries are there? There are n entries, because they are arrays of sizes. So this we are doing n times. So hence the total time that the algorithm takes is order n time. And why is this dynamic programming? Because I'm actually using my small sub problems to build a solution for the bigger sub problems, and I can use optimal solutions for these sub problems to build an optimal solution for my bigger problem. Now you can also in this case, the value, it just tells you the value here, right, that the maximum sum is 18. You can actually do some kind of a backtracking here. You can, if you use some extra memory like order and memory or something extra, then you can actually find out what the subarray is. You can even find out the starting and end index of that, and so on. So it's not very difficult to do that. It's something similar to what you did in the shortest path algorithm. So I'll not I mean, the idea is similar, so we'll not get into it because we want to focus on the strategy right now. I mean, practicing the strategy and understanding it clearly. So we'll not get into it, but you can even try doing that. So you can take it as a homework. So are there any questions about this particular problem that we discussed, the maximum subarray sum problem? Sorry. Okay. So if yeah, so if there are no questions, we'll look into another problem. So it's called knapsack problem. Let me write the problem. So this is called knapsack problem. And what does the problem say? So you basically have some n objects. Okay, so you have item 1, and maybe I'll say item 1, 2, 3, 4 all the way up to n, and there is some value that is associated with the object. So that means maybe object number 1 is some diamond and it has a lot of value. So let's say the value is 100 for me. Maybe item number 2 is some stone which may be not that valuable, so the value is 5, and so on. So there are some arbitrary n items and there is some value. Let's assume it's positive. Okay, positive. Let's not assume it's negative right now. Okay, so let's say you have some values that are associated with each of them. Okay, and there is also some weight, so they also have some weight. So for example, the diamond that you have here, okay, it has a value of 100 but it's also heavy. So it could be that this weighs some 30 units, and let's say this item 2 is not that valuable but maybe it's not very heavy, so let's say its weight is 1, and so on. So it's not necessary that valuable item has less weight. There's no correlation. I'm just arbitrarily writing any numbers, 2, 15, and so on, let's say. So what we know is there are some n items that are given to us. They have some value and they have some weight. Let's now assume that none of them are negative. And what you have is a sack. So you have some sack here and it has, you want to pick this item. So you're going to pick this item 1, put it here. Pick item 4, let's say you like it, you put it here. So there is one catch though. Your sack has a capacity. It can't hold more than some amount of weight. So let's say it can only hold weight up to W. I can't do more than that. So now there is some kind of a constraint. I can't just arbitrarily take any item and keep on putting. What I want to do is I want to maximize the value that I can have. That is the most natural thing to do. So there is some constraint on weight, but I want to respect that weight constraint and still achieve maximum value as possible. So let me just write this in terms of input output form. Input to you is an array of n items. They have some weights, they have some values, and there is a maximum capacity of W. And what you want to output is the maximum value that we can attain by picking some n items such that their total weight is still at most W. And let's say for now, let me just assume that there is an infinite supply of these elements. So I'm not saying that this item you can only pick once. You can pick it as many times as you want. Okay, there's no limit on the supply of them. They're unlimited, but you can't pick all of them, of course, because there is a weight capacity. So this kind of a constraint is called unbounded. This is unbounded version. So I'll just write it here. Okay, what do I mean by that? You can pick items, as many items of the same kind as you want. Okay, so is the problem clear? Okay, so yeah, so just to summarize, you have these items, you have weights and values, and you have a capacity. You want to respect the weight. You can't make the total weight more than W, but you still want to maximize the value based on these constraints. So what is a natural strategy that you can have to solve this?
Ma'am, we can sort their array according to their value and then fit it until it gets full.
Okay, so if you sort them according to the value, then okay, so then yeah, let's say you sort them and let's say the capacity is let's say 60 for me, and then the values are like this, 100, 30, but then if I do 15, then I can make 75, and if I do um, yeah, maybe I'll just say, you're saying sorting on values or sorting on weights? Sorting on values, right?
Yes, ma'am.
Huh. So let's say this is one example that I have. Then if you sort on values, what will happen is you will pick this item 1, and the current value you have is 100, the current weight you have is 30. Now I still have a capacity of 30 more that I can take. So again, because it's sorted and you're allowed to make multiple, you're allowed to take multiple times, you will again end up taking 100 and a weight of 30. So eventually you have gotten total value of 200 within the weight of 60. But let's say I don't do that. What is the maximum I can do by using this? If I just pay 3 units of weight, I can get a value of 75. So I'll get 75 into 20, which is 1500, which is a value of 1500 if I don't use this, if I just use this. So um, yeah, so this is a counter example, right? Because what's happening here is, although its value is not as large as the largest as the other one, I'm still paying a very small price. The weight is very small, but it's adding a lot of value with respect to it. So I'll just take these kinds of um yeah, these items, and then that will beat the greedy type approach. Is that clear? Is it clear why it will not work?
Yes, ma'am.
Okay, good. So then what can we do? Any other ideas? Or can you try identifying a sub problem here to solve the bigger problem? Okay. So greedy approach about using value over weight. So okay, so let's do this. What Ramanathan is suggesting is that you'll be greedy. So, and what you'll do is you'll find value over weight of an item. So let's say value was 100, 30, and you had 75, and what was this? This was 3. Then you had, let's say, 20, and maybe let's say 10, 4, and 2. So then what we'll do is we will find out this value over item. So what is this? This is let's say 10 by 3, 3.33, something like this. This is 25. Yeah, 25. This is 2, and this is 2. Okay, so what he's suggesting is that you find the value over weight of this. So that means what is the item for which I can get maximum value by paying as sorry, this is not item, sorry, by paying as small um, weight or as small cost as possible. So in this case, that is 25. So then what he's saying is you just keep taking these 25 of um, yeah, of these, and then you'll end up getting the maximum. Okay, but okay, so let me come up with the counter example. So hmm. Okay, so maybe this is maybe not a very good example, but let me try to come up with one example like that. So hmm. Okay, so basically the problem can happen when the weight that you have is not divisible by this number. So let's say the weight is something like um, 76, and let's say that, yeah, let's say I have 3 here, let's say 3 here, 9 here. So okay, this is still okay. I don't know if this is the exact counter example, but okay, I'm trying to say that the problem will arise when, let's say you take 25 and you're going to take two items of these, and that will make a weight of 50. And yeah, let's say this does not exist for now. Yeah, and then you this makes a weight of 50, and you have a value of 150. Okay, and now you have some 16 of these, yeah, sorry, some 26 weight that is remaining with you. Okay, so you'll actually take, sorry, you'll take 3 of these. Well, just do 74. If you take 2 of these now, then you have a weight of 50, the value is 150, and you have a capacity of 24 that is left with you. And this you cannot satisfy using um, yeah, using these, but yeah, but you can use this to fill up the rest of them. So this is not a counter example yet, but what I'm trying to say is, if the number is such that by taking these values, you'll eventually end up with some number which is remaining, which you can't satisfy using these weights because it's very large, but you also don't have the remaining items to fill that weight. Okay, which can happen if, for example, this is larger than um, maybe you have some 23 remaining here and this is some 24, then you can't even use this. So there is a whole lot of capacity that is going wasted because you made a greedy choice here. But if you would have taken this smaller and smaller items, maybe some combination of these, such that their combination adds up to the value, the exact value of the weight, and therefore even though you are losing on the values of these items by small some factor here and there, you're losing something by not taking the largest one, but because I'm able to fill the whole gap, there's nothing in the sack that is going wasted. Maybe the total capacity of the total value of these elements now is I mean, the total value is still larger, it surpasses than this. So I mean, am I at least intuitively conveying the problem with this? Although I don't have a counter example ready, does this convey what is wrong? Ramanathan. Okay, so I'll just try to explain it one more time. Although I don't, it would have been nice if I had a counter example ready, but let me try now. So let's say you have some capacity of, let's say 75 again. Sorry, what was that? 74. Okay, let's say there is some capacity of 73, and you have some items of this weight, this value over item of 25. And yeah, so what you did was you took those items, you packed those heavily. So what I mean by this is you are occupying this much of weight, and you kept on doing as much as possible, and now there is some gap in the sack, there is still some capacity that is remaining. Okay, but I can't use this big item because I don't have that much space. But the problem also is that I can't use the remaining smaller items because they are also not large enough to um, I mean, sorry, they're also not small enough to be covered here, because the gap that is left is so small that now none of the items can occupy it. So there is some space here that is going wasted. Okay, so there is some greedy thing you did to try to optimize. So there is some value you got here. Okay, but then there is some space wastage happening. Okay, so this is just intuitive because I don't have an example ready with me right now. But I'm saying what you could do is, maybe I'm not being greedy. I'm actually looking at some items for which I'm actually paying more weight, more weight for the value. It's possible maybe it's not optimizing. But what is happening by doing that is, if I look at the sums of these weights, maybe they are like optimizing the space so much that maybe some combination of items here, they're optimizing the space so much that there is only limited wastage that is happening. So do you understand what I mean by, I mean, you understand, right, what I mean by this, at the wastage part? Okay, good. So now I'm saying that it is now possible that if you sum up these values, although I agree that these are not as value worthy with respect to the weights as these, but what happened is I managed to pack up a lot of those items now. And therefore, as a collective sum, maybe the sum of this total sum is now actually greater than this value v1 that you had here, because there is very minimum um, space wastage that happened. So I managed to pack it very fully, and therefore now if I add the values, I can actually get more. So this is not always possible, but you can come up with examples like that. So now is this okay? Okay, good. So do try to come up with this, but this is actually a very nice strategy of doing this. So can you come up with a scenario where this will work? So can you just modify one constraint in this whole example? You just have to relax one constraint so that this greedy approach works. So there is something here that's not allowing me to do this, right? So this wastage that is happening is not allowing me to do that. So how do I relax that? Why is this happening? Limited item, you have unlimited items, but the problem is that you are allowing me to only take integral number of them. So I take an item, I take whole of it, I can't take half of it. If I allow you to take fractional item, then what you could do is, maybe like this weight, this is um, maybe yeah, maybe this is like 10, and the weight of my most valuable item was 15. So earlier I could not do, but now I'm saying something like you take 2/3 of that item. So then if you do 2/3 of 15, you will actually fill this whole thing. So you're not taking the whole item, but you're taking 2/3 of the item, and therefore you are able to now fully use the sack, because I'm allowing you to take fractional values. So this is called fractional knapsack, where you can actually um take any fraction of item. So it need not be integral, you can take fractional many items, which right now does not make sense if you think of these as discrete item, but there are scenarios where it makes sense. So this is indeed a valid greedy, I mean, this is a correct solution for a for a fractional knapsack problem, which is a greedy strategy. So but it will not work in the case when um, I'm imposing integral constraints, that an item will either be taken or not be taken. You can't do like taken half or something like that. So is this clear? Okay, good. So now we know that this does not work, or although we don't have an example, I couldn't give one yet, but if I come up with something, I'll add it into these notes before I publish, before I post it on the drive. Okay, but yeah, believe me on that for now. And can you think of some DP, some dynamic programming sort of, or like a sub problem that you can use to solve the bigger problem? Okay, so let me just define the variable. Maybe that will help you to identify the subproblem. Okay, so let me say that m of w denotes the maximum value that we can get when the knapsack has capacity of w remaining, or let's say remaining capacity of w. Okay, so that means I have a capacity of w that is remaining with me, and I want to find the maximum value that I can get for that particular knapsack. Okay, so how do we do that? So um, this is going to be maximum of yeah, so let's say my items are I1, I2 up to IN. Their values are V1, V2 up to Vn, and their weights are W1, W2 up to Wn. Okay, so if I take the first item, then I'm already getting a value of V1 with it, right? So the total value will have this uh, plus, now it's same as solving the problem for weight w minus w1, because in the whole knapsack that I had, I've taken this item 1 and I'm already occupying the weight of w1 from it. So the remaining weight I have is now w minus w1. So it's same as optimizing, finding maximum value that I can get for this particular part of knapsack, and the value that I get for this, if I add it with the value of first item, I'll get the value of the whole thing. So this is just saying that find the maximum value for the smaller subproblem and add it with V1. That will be the value of your whole knapsack. Similarly, I don't know which item to take, right? It could so happen that maybe taking the second item actually gives me better. Maybe I don't taking first item is not good for me. Maybe second item is better. So V2 plus m of w minus w2, and so on. Same thing happens for V3 and all the way up to Vn plus m of w minus wn. So then to solve this, we are recursively going to use the same formulation. So m of w minus w1 will be max of, you do the same thing again and again. So is this formulation okay? Is this equation, is this relation making sense? What we wrote here, do you want me to repeat it? Okay, so if it is clear, then can someone tell me what is the value that I want to find? What is the final answer? What is the value that I should write here, which will give me the solution for the problem that I asked? Okay, so what does m of capital W denote? By our definition, it means what is the maximum value we can obtain for the knapsack whose capacity is capital W. And this is exactly the problem that we asked, right? You have this knapsack with capacity of W and you want to maximize the value. So m of W is precisely denoting what I want to find out. So then what it will do is basically it will take this m of W and it's going to find m of w1. So v1 plus m of w1, v2 plus m of w2, sorry, and so on, vn plus m of w minus wn. And then I want to find a maximum value for this, right? So then you are going to explore this again. So this will be v1 plus m of w minus 2w1. This will be v1 plus v2 plus m of w minus w1 minus w2, and so on. So when will this terminate? If this weight eventually becomes negative, that means I can't add that item. Then you will just simply write a 0. That means you can't take that item. So yeah, so then you will terminate. So this is how the recursion tree will look like. Okay, so is this clear? Okay, so okay, so you can even you can do both implementations of it. You can do a memoization version of it, you can even do an inductive version of it. So if you write it like this, it, yeah, I mean, this is the recurrence relation you have, and then the base case would be that m of yeah, so m of w1 would be um, yeah, would be v1, and so on. M of w2 would be v2, and so on. And m of some weight w where w is less than 0 is 0. This is just to make sure that the weight cannot go negative. If it goes negative, then you just write 0 and start terminating from that branch. So yeah, so if that is clear, then try the same example but with yeah, but now I don't allow you to repeat the objects. So if you take an object, you're going to take it at most once. You cannot take it multiple times. So this is the bounded knapsack version. Where an item I can be taken at most once. So then what is the strategy? How does it change? Any ideas how we can modify the previous answer? Okay, so let me just give a hint and then you think about it. Let me know if you have any ideas that come up. Okay, so okay, so earlier what we did was we denoted m of w by the maximum knapsack weight, um, I mean value you can obtain, value that can be obtained by with weight, with capacity at most w. Okay, and now why this does not work? Okay, first of all, is it clear that the same thing does not work, right? Because in the previous one you could have optimized by taking the same item again and again, which is not allowed in this case clearly. So then what you do is we're going to modify our variable by saying that m of iw is the maximum knapsack value that can be obtained by choosing items up to I. That means I have labeled my items with the numbers 1 to n, and I'm only allowing you to choose from items whose label, whose number is at most I. So when I say that I is 3, that means you can only choose from items 1 to 3. So this is what the I represents, and the capacity of the knapsack is at most W. Okay, so now using this, so you might have noticed by now that this extra I that we introduced is something similar to what we did for the all pair shortest path. So just to show you, so this extra k that we had introduced there is to tell you that you are allowed to use the nodes whose label is up to k, and then you go from k to k minus 1. And yeah, sorry, this should have been k minus 1, that, yeah. So that's how you keep on reducing this sub problems from k minus 1, k minus 2, and so on. So this is the same idea that we used here. So I'm just introducing one more variable to tell uh, which items are allowed to be taken. So then if the meaning of this is clear, can you tell what is it that we want to find? So the quantity we want to find in terms of the new variable, what is it? M of so W is just the capital W. It is the capacity that is given to you for the knapsack. But what is I here? What are all the items that I'm allowed to use? I'm allowed to use any of the n items, right? So initially I'm allowed to use any of the n items. So this is simply m of n comma w that I want to calculate. Now how will I do that using my DP approach? So DP approach says that m of I comma w is the maximum of either I take the ith item or I don't take the ith item. It's possible that taking ith item gives me the maximum. So these are all the items you have. Maybe taking this is going to give me the maximum. In that case, let's say I take the item. Then what is the value that I get? The value I get for that is Vi plus, then I want to maximize the remaining weight. So this is m of I minus 1. And what is the W? So what is the weight that I now have to maximize? So this is similar to what we did earlier just now. So W is the total weight I have, and I've already picked the item I. So the weight for that is Wi. I'm already paying a weight of Wi for that. So what is the remaining weight I have? I have W minus Wi. So this is W minus Wi. Or it can so happen maybe I get the maximum by not taking this ith item. In that case, I'll not take it and look for the new maximum by looking only at the previous items and then the weight does not change because I did not take that item. So is this clear, or are there any questions about this? So compare this with the previous relation we had, and see how it is different from this one. So just let me know if you need further explanation on this. Okay, so let me just repeat this one more time, although, yeah, just for the sake of making sure that everyone has understood. So, what we did was we let this M of IW denote maximum weight you can value that you can get in the knapsack, whose capacity is at most W, but you are only allowed to take items which are labeled from 1 to N, 1 to I. Anything that's greater than I will not take. So what is our problem? Our problem is I want to maximize the total value where the weight that is given to me, the capacity is bounded by capital W, and I'm allowed to choose any items from 1 to N, but I can't take them multiple number of times. I can either take them or leave them. That's it. So then what you do is you look at so this is what the quantity that we defined earlier, which I want to maximize. So when will I get the maximum value in my knapsack? It is either that I choose the ith item. In that case, the remaining weight that I have here is W minus Wi, and this I want to maximize. So that is nothing but M of W minus Wi. And what are the items I'm allowed to use? I've already used the ith item, right? So then if I'm allowed to use only from items 1 to I, which is what we said here, it comes from there, and I've already used the ith item, then I'm anyway only using from 1 to I minus 1. Therefore, I write I minus 1 here, and by adding this ith item, I've already paid a value of Vi. I'm already getting a value of Vi. Therefore, we are adding the value of Vi to the maximum value you can get for this subproblem. Or it can also happen that I don't have to take the ith item. I have to leave it in order to maximize. In that case, what will the knapsack look like? It will look like the same. I still have to make a total weight of, still have that capacity, but still I'm not going to choose I because I took a decision of not taking it. Therefore, you have an I minus 1 here, but the weight remains the same because I did not take that item. Hence, I did not lose any weight, nor did I get any value. So, there's no addition of Vi, there's no subtraction of Wi. Okay, so is this clear? Then we can have base cases based on whenever I minus 1 becomes 0, you just make the value of the whole thing 0, and whenever it's 1, then it's simply the value of W1, and so on. So you can so you can have the appropriate base cases. That's not very difficult to do, but the main idea here is to understand how do we get this recurrence relation. Once we have this relation, you can do both versions. Okay, so yeah, so if there are any questions about anything that we discussed so far, yeah, feel free to ask. Okay, so if there are no questions, we will do one quick application of Knapsack. So this is one quick application of what we saw just now. So I'd say this is the coin collection problem. Okay, what does that mean? I have some denomination, so I have some coins with me. Let's say I have rupee 1, rupee 3 and something like that. So I have some, so I mean, just don't worry about whether they exist or not. I'm just writing some random numbers here. I have some denomination, some coins here. Okay, and I want to make a total of 100 rupees with it. So how can I do that? Either I can take all 1 rupee notes. If I just use 1 rupee coins, all rupee 1 coins, if I use, how many do I need? I need 100 of them. But if I use rupees 10 coins only, then I only need 10 of them. Now 100 is a nice number where you can divide with all these, but let's say if I had something like 96 here or something like that, then there are so many combinations that you need to consider. So the question is, I want to make a total of some value. So I have to make a total of some rupees r, and I have to use these denominations. I can use them as many times as I want. So this is, you can think of this as an unbounded version of Knapsack, where you are allowed to take the item as many times as possible. But what I want to do is I want to minimize the total number of coins that are used. Okay, so in this case it's very obvious that if I use all rupee 10 coins, then I'm going to make a total of 100 by just using 10 coins. So in general, if I just give you some rupee r, I want to, and these are not the exact denominations that are given to you, this could be any numbers, any non-zero numbers. Then let me say x1 x2, or let's say p1 p2 p. So the denominations you have are of values v1 v2 up to vn. These are the n coins you have with different values v1 to vn. You can use them as many times as you want, and the total you want to make is total sum that you want is that of rupees r. And what you want to do is you want to minimize the number of coins used. So how will we do, how can we use dynamic programming to solve this? Or you can do freshly, you can solve this with a fresh perspective, or you can use what we did earlier. So this is similar to Knapsack, but you have to think of this problem or formulate it in terms of the Knapsack problem, and then you can just simply lift the solution for the Knapsack problem to solve this problem. So either is okay. So just take some time, maybe think about it for a couple of minutes, and let me know what you think. So then I'll just wait for some time. So any ideas if you have, feel free to write or unmute and let me know. It's not necessary that it's on the correct lines. Any idea is a good idea. Okay, so one thing you can do is, of course, you can try to make your own variable and define a new definition for it, and define the relation, recurrence relation, and so on for it. That is something you can do. But what I want to do is, I want to think of this problem as an application of okay, as an application of the knapsack problem that we had. So then what I want to do is, if I want a knapsack problem, then I can think of this as a sack that I have, whose capacity is r, because r is what I want to make. So the capacity, or the w that I had, the capacity W, so I'll write this as knapsack formulation. And the capacity W corresponds to the value of R here, because R is the total number of amount that I want to make. And the values V1, V2 up to Vn, these are the same as the amount the denomination has. If the coin is of rupee 1, then V1 corresponds to 1, and so on. So it's basically the value that the coin has, that's written on the coin. And what are the weights of the coin? Because this is something we had in the knapsack. So um, so notice that the weights correspond to the fact that we want to minimize the total number of coins here. So earlier, um, so can you think of something? Can you think of what should I assign to W1, W2, and so on? Because with the coins, I don't have weights associated with it. They are all equal for me, but I want to minimize the number of coins that I use. So um, if I think of these as weight 1 coins, if I think of them all having weight 1, that means I want to use as few coins as possible. So is this okay? So this is basically same as the knapsack problem. Also, the question is whether it's unbounded version or the bounded version. So in the bounded version, you are only allowed to take it or leave it, but in the unbounded version, you can take it as many times as you want. So in this case, we said you have infinite supply of coins. You can take, if you want 10 rupee coin, you can take 10 rupee coin. There is no limit on the fact that you can take it only once. Therefore, this is the unbounded version. So this is also something that we identified. Therefore, what you have now is an instance of a coin collection problem, and we have converted it to an instance of unbounded knapsack problem. And whenever we say knapsack, we mean integral knapsack. If I want to say fractional, then we will specify that it's fractional knapsack problem. Okay. So this is something that we did, and now we will simply use our solution to the bounded knapsack problem, which is this. And then we'll use this DP solution to to solve the problem. So just if you get the idea, then can you roughly find out what is the running time of this? What are the parameters that it will depend on? Roughly what is the running time? Okay, so so let us see. In the previous case where we saw this subarray problem, it was something like order n, it was linear. But here you have something interesting happening. So notice that here you have a weight which is coming into play. The weight capital W, M of capital W, which you want to find out. So if W is very large, so for example, if W is like say 10 million here, and the denominations, let's say the coin problem, W is 10 million, so I want to make 10 million rupee amount, but let's say I only have the maximum coin that I have is of value 10 rupee 10. So what will this formulation do? It will just subtract rupee 10 from the 10 million. Then from the remaining amount, I'm again going to subtract 10 rupee, and so on. So this will happen like how many times? This will happen 10 to the 7. This is the amount I had, divided by the largest denomination I have, which is 10. So this will happen like a million times. So 1 million times you are going to keep on having to subtract 10 rupee 10 each time. That means the running time of the problem depends on how large the weight is. If the weight was very small, if I just have to make 20 rupee, I would just do 10 rupee, I'll just take my 10 rupee coin, then I have a remaining weight of 20 minus 10, and which is 10. I'll take another 10 rupee coin and I'll be done. This just stops in 2 steps. But if the value is very large, I have to keep on doing this again and again. So this kind of algorithm, so if you analyze this, actually the running time of this turns out to be order n times w, where n is the number of items, w is the weight that you have. So generally all the algorithms that you have seen so far only depend on the length of the array, or let's say yeah, basically the size of the input. But this is the first instance I think you might have seen where it also depends on the value of um, some other parameter. So these kinds of algorithms are called pseudo deterministic algorithms. Why is that? Because they are deterministic, pseudo polynomial time algorithms. So why is that? Because they are the rest of the factors are polynomial. If you ignore this w, the rest of the time is polynomial in terms of n, but there's this extra factor which is the value of it, because of which you call it pseudo polynomial, which means if that value is very small, then you are actually running in polynomial time, but if the value is large, then you are actually doing worse. So yeah, you can actually write an algorithm for this with all the base cases and actually see that the running time turns out to be this. And there are again several applications of knapsack problems. So there are lots of problems that can be converted into a knapsack instance, and then you can just simply use the solution to knapsack to solve them. So few resources, few nice again same references where that I've been pointing out I think throughout each week. So same references, you can use this um, Papadimitriou, Dasgupta, Papadimitriou book. This is called Algorithms. Then you can again Kleinberg Tardosh also has and CLRS, of course. So all the three books are a very good resource for studying dynamic programming, and they also have lot of examples to practice. So if you want to practice more, then these are some good resources. And just one more thing I want to mention before ending the session is that you know by now that greedy algorithms are good, but they don't work all the time. They may work sometimes, but they don't work all the time. Sometimes you're doing really bad by just being greedy. And same thing happens with dynamic programming also. Not every algorithm has not every problem has a dynamic programming approach. Sometimes it may work, sometimes it may not work. It can also happen that DP and greedy, both of them work together for the same problem. Maybe different sub problems are being used, but they are still good. They can both solve the problem. It can sometimes happen that greedy works but DP doesn't work, or other way around. But there are also problems where none of them work. Then you have to do something tricky to solve them. So what we'll do next week is we'll call these hard problems which we don't know how to solve efficiently. So this kind of hard problems, if you come across it, how do we classify them, how do we identify them, and if they are hard, then what can we do to if we come across them. So do we just leave it, or do we come up with something else creative? So these kinds of this intractable problems, and how do we deal with them? So this is the lecture content for the week 8, and we will also look into some nice problems on this for in the next week. So next week again we are meeting on Friday, same time 6 p.m. to 8 p.m. and after that I think the final class would be on the summary class would be on the Monday, the upcoming Monday, which is I think 17th March, I think. Okay, so I think we'll meet on 7 p.m. 7 to 9 p.m. There will be announcements that will be made, but I just want to announce it one more time. So if there are any questions regarding what we saw today, I'll wait for some time. Otherwise, feel free to leave, and thank you for joining.